Good morning. This is Bill Segment, Director of Sales Engineering for phoenixNAP. Today, our guest star is Alex, Engineering Program Manager with HPE. First poll question, we've got a couple of them here for you. What type of cloud deployments are powering your most data-intensive workloads? We're going to give everybody a little bit of time to answer that. Seeing lots of hybrid and multi, not very shocking there. Second question would be, what percentage of your workloads are cloud native? If y'all wouldn't mind taking a minute to answer that. Very good. Okay, let's get into it. So here's what we're seeing out there today. The biggest thing we're seeing with the hyperscalers is most folks on the public clouds are over budget, and most of them just kind of have what we call widespread misuse of it. Too many people have logins. They start getting a lot of waste just because people spinning up, tearing down servers. They'll spin them up, they'll forget to tear them down. Nobody knows who owns what, that kind of thing. Obviously, public cloud growth is going to keep going. The big thing now is for most folks is to figure out how to get a cap on that spend, to reduce some costs, and then cap that cost as well, so it becomes more predictable. And that's kind of where the ARM servers come in. Very predictable for your workload. You don't have stuff underutilized or overutilized. We're going to get deeper into that now. So let's talk a little bit more about ARM and why it's great. So obviously it leverages risk computing. That helps us because you get efficiency per clock cycles. So that breaks down into faster speed with parallel processing. That means you're able to do things like microservices much more consistent and stably. Most folks agree they need their services right-sized. Obviously, you need to know your workload and what size you are required to have for that. Obviously, a lot of folks want to implement CI/CD, and we have tools for that. We're going to show you that a little bit later. As we just saw in the poll question, most people are doing hybrid or multi-cloud to try to reduce costs and to try to streamline efficiencies. And we're going to talk about how ARM's going to help you do that. And with that, I'll hand it over to Alex. Over to you, sir.
Yeah, thanks, Bill. Yeah, my name's Alex Eslaks, and I'm an engineering program manager at Hewlett Packard Enterprise, focused on our compute products, and excited to talk about our RL300 today. So I'm sure many of you guys know phoenixNAP inside their bare metal cloud offers the A1.C5.large instance. So I just want to take a moment to kind of open that up and look at the hardware layer underneath. And that's powered by HPE's ProLiant RL300 Gen11, as you see here. And I'll briefly introduce what it is at the hardware layer and why it offers a really great performance for cloud native workloads. And of course, like I mentioned, it's available today. Very briefly, what is the RL300? Just at a hardware layer, right? It's a one-use single socket pizza box server, if you will, powered by Ampere Computing's Ultra 80-core CPU. And then, of course, is powered by itself is powered by ARM's AR64, 64-bit Neoverse N1 cores. And so this platform is really, really great for what we'd call cloud native workloads. And what does that mean in a nutshell? I would say number one, they'll tend to be Linux native. And number two, they'd be workloads that you would typically containerize. You'd be usually running Docker or something like that, orchestrating with Kubernetes. And they'll tend to be workloads that inside of these containers, they'll scale up to some level of performance, and then you'll scale out by adding more containers of the same kind of application. Let's say poster child or the prototypical example would be Nginx. So if you have a web server, basically you'll serve X number of HTTP requests, then that container or that instance of the website is saturated, and then you'll just deploy another one. It'll serve basically the same amount of HTTP requests. But there's really a large number of workloads out there that would fall into this category, right? You see a few of them here, Nginx, MySQL, Redis, Memcached. I'd really encourage you to go Ampere Computing. So the CPU vendor has a really fantastic resource. If you just Google Ampere CPU briefs or Ampere Computing briefs, the link is here. I'm happy to put that in the chat as well. But this is really a fantastic resource that says, okay, what the heck is a cloud native workload? What would run really, really well on this platform? And then if you drill into it, right, you can click, and each of these briefs will have some really compelling performance data based on that workload. So if you find a workload in that list, it's going to be really great. This is just a kind of a general introduction, and things like this will tend to run really well, right, as those cloud-native workloads. Why is it that the RL300 and A1C5.large is so good at these cloud-native workloads? Why is it just really, really compelling, high performance for these workloads? So there's 3 core design elements at the hardware layer that we're really excited about in the RL300. So number one is inside of the Ampere CPU, every core is just single threaded. So there's no simultaneous multi-threading, no hyper-threading. And then secondly, every core has a constant 3.0 gigahertz clock speed. So these 2 factors at the CPU level is paired with a design choice that HPE made at the server level, which is single socket design. And that means that there's no NUMA, there's no non-uniform memory access that would introduce, let's say, unpredictability or jitter or latency that we'll see in the following slides. On the next slide here, we say, well, this kind of talks a little bit about these cloud-native workloads. Like I mentioned on the left, you have a traditional monolithic application where a lot of the different functions are written into one giant piece of code, one giant application, whereas more modern so-called cloud-native applications tend to have a microservices architecture. They'll tend to be containerized. And each of these microservices will then have their own function, right? And then the software application will be a combination of a lot of these little microservices talking to each other. But you can kind of envision here with all these lines, right? You have to stitch all of these containers, all these microservices together, right? They have to talk to each other through APIs. And the 2 things that you would really want, if you're stitching together lots of very small microservices, is I think most obviously you're going to want low latency, right? You want all of these microservices to be able to talk to each other very quickly, but perhaps a little more subtly, and we'll see in just a moment, you also want very low jitter, right? You want the latency to be low, but you also want it to be predictable. So the latency between these microservices is consistent in addition to low. We can illustrate this with some really great data from Ampere. So on the left here, this is just using an example workload. So this is a P99 latency for Redis. So we saw one of those. That was one of the beautiful graphs we saw at the beginning in terms of sheer performance versus x86. But this drills a little bit deeper. So on the x-axis here, you're scaling up the loading or the utilization of the CPU, right? In this case, Ampere Ultra's 80-core 3.0 gigahertz part, which is exactly the CPU that's inside of A1C5.large. And then on the y-axis, this is just the latency in terms of microseconds for this benchmark. And obviously we see, so the red line is Ampere, kind of the greenish line is an x86 competitor. So the most obvious thing is, oh, hey, that red line is much lower, right? So as the platform loading, the workload scales up and utilizes more and more of the CPU's capacity, the line is much lower than the green line, right? And it's consistently much lower the whole time. And that's obviously showing that it's lower latency in general, right, across the full utilization of the CPU. And then secondly, the thing that probably jumps out at you is, hey, it's a lot less squiggly, right? There's a lot less flatness for the green one. You can see the little illustrations here. So as turbo kicks in, or the boost frequencies, so the frequency of the core is changing dynamically with the loading of the core. And then SMT kicks in, so now you're starting to utilize hyperthreading. This introduces a lot of the jitter, right, that I was mentioning. So not only is the line consistently higher with higher latency, but it's much less flat. So as these features, which can be suitable for some general purpose workloads, kick in, it introduces not only higher latency, but much higher jitter. You'd say, well, how do you quantify that, or how can you really demonstrate that? Because the graphs we're looking at before, Nginx, Redis, et cetera, they're really great. You see this is fantastic performance, but those workloads are just saying, like the Nginx example I provided, that's just saying, well, hey, here's one container of a given Nginx, website, and it'll be saturated after X number of HTTP requests. So you just deploy, another instance, another clone of that same website, and the performance will scale out linearly. And that's great, right? That's a good benchmark so far as it goes. But there's another really great benchmark called Death Star Bench. And this is also, by the way, available in that Ampere Computing/Briefs website if you drill down. This is kind of a simulation of a social network application. But the key point here is you can see the Work2 HTTP load generator on the far left. It's going into a number of different containers, right? Different microservices that are doing different things. You have all the way from your load balancer through your Nginx front end, through a lot of kind of plain Plinko, if you will, right? So this simulated user is, you can say, you submitting text in a something like X or Facebook, something like that, or they're requesting a post in a cat video, something along those lines. And then it bounces all the way back, and you have containers on the back end that are doing caching and storage with Memcached, Redis, MongoDB, and then that request is coming back to the user. So this is a little bit more real world simulation, because instead of lots and lots of identical clones of the same container, which is kind of what we were seeing earlier, this is kind of a mix and match, right? It's a heterogeneous hodgepodge of a lot of different microservices and how they're all kind of playing together, right? So when you deploy this kind of benchmark, a little bit more real world benchmark, we see the results on the following slide, which, as you might expect, are absolutely beautiful in a nutshell. So basically here on the far left, you have the P99 latency. So lower is better, right? The latency of the request throughout the whole system. So not just a whole bunch of Nginx containers scaling out, but all of those different kind of heterogeneous microservices that are playing or interacting with each other. So the latency throughout the system is much lower, which is exactly what we would want and what we would expect based on those three hardware benefits that I mentioned earlier. And then that also translates, as you see in the middle, to much higher throughput for the system. So the system itself is not only serving each individual request is snappier, much more performant for the end user, but a corollary to that is also that the system can serve a lot more requests, right? Within a given unit of time or within a given kind of SLA, right? And then all of that combines on the right. So this means versus x86 competitors, the total system provides not only superior raw performance, as you see in the left and the middle, but also provides far superior performance per watt, as you'll see on the right. And all of that really translates, to users of phoenixNAP's bare metal cloud as it's lower TCO for phoenixNAP, which translates basically to a lower sticker price for you when you reserve it either by the hour, by the month, by the year. And it's really, really compelling in terms of not only its sheer performance for these cloud native workloads, but it's also really compelling in terms of the performance per watt, right? Or in this case, performance per reservation dollar, if you will. So that's looking kind of at a general purpose, this Death Star bench. If we look at and comparing to x86 competitors, right? There's a couple of open source benchmarks out there that you could just Google, or I could throw in the chat if there's any interest. And these are out there kind of live on the web, and this is third parties that have taken the same CPU, the Q8030, so that's the 80 core, 3.0 gigahertz CPU, and they've compared it against other ARM cloud offerings out there. And in this case, Graviton 2, which is 64 cores and lower clock speed. And this particular benchmark, CF benchmark, is open source. This was published by Cloudflare on their blog. I just snagged it from there, but it's public knowledge. The benchmark itself is published on GitHub, so you could go run it yourself if things like OpenSSL, LuaJT, and these kind of benchmarks are interesting to you. But I think the takeaway here is if you go head-to-head or core for core, Ampere Ultra's 80-core CPU outperforms AWS Graviton 2 on a single core basis, as you see on the left. And because it's performing better core for core, and you get 80 instead of 64, as you would expect, it performs even better socket for socket, right? Or CPU versus CPU, the multi-core kind of here in the middle. And again, you can visit this online, and you can see how the various categories that the benchmark evaluates, and take a look more deeply there. Some of y'all may be familiar with the benchmark Phoenix. So this is a similar one, also kind of out there in the public, but this is comparing Ampere Ultra 64 and 80 core CPUs versus, again, AWS Graviton 2. And this is, if you look here, it's basically the whole suite kind of going clockwise around, so all of these different benchmarks. And I think the key point to take a look at is you have red here, which is the baseline, so Graviton 2. And then you have green, which is the most performant across all, and that's saying the 80-core Ultra CPU versus Graviton, so socket for socket, if you will, right? The performance is substantially superior across the Phoenix benchmark suite. And then what they did in the blue is it's the same CPU, but they just enabled only 64 of the CPU. So it provides a bit of a, let's say, more of a core for core evaluation. And again, what we see consistently across the benchmark suite is superior performance, not only socket for socket, but also core for core. As we see next, really the key value proposition of phoenixNAP's A125.large powered by HPE's ProLiant RL300 Gen11 server is you can get basically superior performance. So if you have a workload that's running on AWS, Graviton, or any other ARM public cloud instance today, you have full binary compatibility because they all share the same ARM Neoverse cores. So whatever workload you might be running on ARM today, whether that's on-prem or in the cloud, it'll be binary compatible. You can lift and shift and drop it onto A125.large or an RL300, and it'll run today. And number two, this is just a quick comparison for if you look at similar speeds and feeds, right? So not only do you get a little bit better cores and networking for same amount of RAM and onboard storage and so forth, but you get similar better specs for far less, right? The least favorable comparison would be the hourly rate between Graviton 2 and A125 large, and that's less than a third of the cost, and the savings is only better if you compare that against the more modern Graviton 3, or if you compare that against longer reservation periods. So you get better performance, you get much less cost, and you have the shared ARM Neoverse cores, means full binary compatibility, so you can just drop those ARM workloads onto A125.large today. And then as we saw earlier in the conversation, even if you have workloads that are run on x86, if you're in a Linux native environment, which most of these cloud workloads are, I think the ability to lift and shift will be quite simple. The compatibility between typical Linux distribution, x86, and ARM64 repositories is very, very high. Well above 95, 98% of the packages are available on both. So I think that effort will be minimal, and you get a huge raw performance and performance per watt or performance per reservation dollar benefit. And with that, I'll turn it back to Bill.
Thank you, sir. I appreciate it. Talking more about bare metal cloud, where these guys live. So they are dedicated servers provisioned in the cloud. All of our normal, CI/CD pipeline tools work. Obviously we support everything we've got on GitHub, Ansible, Terraform, Pulumi, Python, Postman, whatever your speed or flavor is, we support it out there. As we mentioned before, they can be reserved hourly, they can be reserved monthly, or on an annual contract. So as Alex mentioned earlier, this is what we're talking about today, the A1C5 large. They are on HPE ProLiant hardware. All the things I just mentioned on GitHub do apply to this. So you can spin up, tear down, get state information from them using Terraform, et cetera, et cetera. So tools everybody's using in the public cloud today work with our cloud as well. Your code is portable. So let's talk real quick about use cases. Obviously, AI and data analytics are what's pushing most of this stuff, especially cloud native stuff. But there is ARM native stuff out there as well. So we've got folks, doing stuff, servers for web-based applications for Android. That's a real big use case. We've got a lot of customers doing that. And web and media, especially on the media side, transcoding, it works pretty well for that as well. And of course, database usage. So as I mentioned before, it's easily scalable. If you need more, you can get more, and you can spin up and tear down as you need. You don't have to be in a long-term contract if you don't want to. More importantly, it's predictable cost model. When you look at our bare metal cloud compared to Amazon or any of the hyperscalers for that matter, it's cheaper and it's absolutely less spiky in the way we charge for it. And of course, the reliable networking. phoenixNAP has tons and tons of carriers in our data centers. you're always going to have a path to get there. And we do offer, I want to mention as well, we offer Megaport services and we offer on-ramps for GCP, AWS, and the Microsoft world. So if you need a fast direct connection, we can offer that as well. In celebration of Alex coming and talking to us, we're offering 30% off on these HP servers we talked about. Obviously, you can get that here using the QR code, or you can ask for us to call you and we can give you the QR code. But yeah, so if you want to just dip your toe in the pool and try it, you can get a 30% discount on both hourly and monthly. And that's valid all the way till the end of the year. Should be noted, these servers specifically are only in our Phoenix and Ashburn locations, not in the others. So left coast or right coast, take your pick. And with that, we'll jump to Q&A. So let me see what we got in the questions here. Okay, our first question is, what are the most common mistakes companies make when modernizing their compute infrastructure, and how can these be avoided? I'll let Alex take that one, sir.
Oh man, well, so that's a great question. I think my perspective is a little bit broader than phoenixNAP's, because they're a bare metal as a service provider, which they're a wonderful customer that I work with, and they're actually a member of our Partner Ready for Service Provider program. So they're a very close partner. We do a lot of engineering work, early release work, cutting edge projects or unique projects, including the RL300. It's a very close partnership there. And I think the question that a lot of customers need to ask themselves is, begin with the end in mind. So what do you want out of your IT? What do you want the end goal to look like? And then, do you want to do that in-house, or do you have the resources to support it and do that? Or do you want to, offload that to a service provider like phoenixNAP? And I think a lot of that, it will depend on what the end state is that you want for your IT infrastructure to look like, and how much of that you have the ability to in-source, if you will. So I think in a lot of cases, if managing your IT and modernizing it, moving to cloud native infrastructure, if that's something that you consider a core value add to the business and you really want to invest in, then yeah, you can go buy your own servers, and HP is really happy to do that. But I think in a lot of cases, if customers view their IT as, let's say, just another cost center to manage, or, yes, it's integral to the business, but we kind of don't want to worry about that. We want to offload that to experts so we can focus on, our profit centers and our unique value add. Then I think the first thing I would suggest is, considering cloud providers like phoenixNAP, because you get a lot of the goodness of the underlying amazing ProLiant hardware that I know and love. But you get to offload a lot of that trouble to experts that have already scaled out their data centers and already have, kind of done the shopping, if you will, to get really great prices from folks like HPE and deploy it. If something breaks, they'll take care of it. And again, we get that close technical engagement, so they'll bring, new and interesting products like this to market really, really quick for you. So I'm not sure if that gets at the general answer, but I think I'd say begin with the end in mind. What do you want out of your IT, and then do you have the resources to get there? And then if you don't, then navigate that with specialists and partners like phoenixNAP.
Thanks, Alex. Another question, does a 30% discount include free bandwidth? Yes, all bare metal cloud accounts get 15 TB per region every month. You say it only takes minutes to deploy. The ARM instances really deploy in about 3 minutes with the Ubuntu flavors. With other Linux OSs, it can be up to 10 minutes. So it's very quick. Another question is, what are the available operating systems? As I mentioned before, we've got Ubuntu, Alma Linux, and Rocky Linux. So pretty much all the main flavors are covered there. Last question. This might be for you, Alex. For systems running on x86, moving to ARM doesn't necessarily align with cloud optimization strategies for us. Does phoenixNAP have a similarly cost-effective alternative for x86?
Yeah, I think you guys absolutely do. and I think I alluded to this earlier, we're working on new and cutting edge products and releases. So phoenixNAP is actually one of the first customers on Earth to place a purchase order for HPE's ProLiant Xeon 6 powered Gen12 servers. And I believe you guys had just launched for commercial availability your first instance for customers.
That's correct. Yes.
So that's a great product. So you have the Intel Sierra Forest, was a code name, powered instances that are available. And the way I would frame that is that these two don't really compete. These two are complementary. So as I kind of mentioned earlier, if you already have an application or a stack or a workload that's running on ARM, whether that's on-prem or whether that's in a public cloud somewhere like Graviton or whatever, if you already have that stack running in ARM, is lift and shift, it'll drop in and run on A1C5.large. And I think that's fantastic. You're going to get immediate, you get up and running almost immediately, and your time to value will be really, really short. And the reservation cost is very, very low. So your performance per reservation dollar is excellent. If you, kind of to my earlier point about, do you have the resources to do this kind of stuff? If you're comfortable porting to ARM, because like you mentioned, Bill, those 3 Linux instances already have excellent repository coverage for ARM64 architectures. Very, very high percentage of all the total, tens of thousands of packages available have been ported to ARM already. So if you, as an organization, are comfortable with that lift, you've already committed engineering resources and so on, then again, I think A1C5.large and RL300 is a fantastic, time to value, fantastic value proposition. The place that I would kind of make the delineation is if you have an x86 stack that kind of falls into this cloud native category that we touched on, but you haven't ported it to ARM, or you're not comfortable, you don't have the resources, you're kind of scared or spooked about trying to port it to another universe, then I think Sierra Forest powered instances would be a really compelling option for you. And they're a little bit newer, so they have DDR5 memory under the hood and so forth. So they'll have a little bit of a performance advantage. Just anecdotally, kind of in the lab myself, I ran that same CF benchmark on an RL300 and one of our new Sierra Forest servers. And I saw, I'd say, modest, per core advantage, performance advantage for Sierra Forest. So I'd say moderate per socket advantage, simply because there's more cores per socket, right? So there is a performance edge, but then I defer to customers to go into the bare metal cloud, and you can kind of costs check, right? You can compare A versus B, whatever reservation period you're looking at, whatever the latest instance prices are. There's also a price premium for that, right? So if you want the most cutting edge performance and you're at a bit of a performance or price premium, or if you want, if you have an x86 stack that you have not, or you're not willing to port to ARM, then I think Sierra Forest is a fantastic value proposition. And again, if you already have a stack that's run on ARM today, the cloud native performance you'll get and the performance per reservation dollar you'll get is just absolutely outstanding on A1C5.large.
Thanks, Alex. Another question, does phoenixNAP and HPE provide porting assistance to help AWS customers port their code to phoenixNAP instances? Sort of would be the answer to that. We have very many code examples out there on GitHub. And again, that's just github.com/phoenixNAP, where you could easily figure out what you need. We also have an extensive library of documentation, so you'll see what differences there are, but we don't actually offer services to port over. But most folks can get there pretty quickly with our examples in our GitHub repository, absolutely. And with that, we appreciate your time as always. I hope this was useful for you. And thanks again to Alex from HPE for helping us out.
Thank you so much, Bill.
Thank you.